Okay, hello everybody. Sorry for this slight delay. Okay, I'm assuming I'm audible. Somebody can say yes.
Yes.
Yes. Okay, excellent. Let me share my screen. Okay, so before we start, so I posted a set of assignment and problems. So what we could do is you can have a look at those problems. How is it for you on Thursdays? Will you have a time open for a TA session? Hello.
We have some slot on Friday available, free slot, sir.
Thursday is not available.
Thursday time series class and time series TA session both have been scheduled.
Oh, this Thursday. Oh, okay.
This
Okay.
Thursday, yes.
Okay. Let me check then what I can do with that. So one of these days we can have a session. Friday, what time suits you?
Friday, I think
5:30 to 7.
5:30. Yeah, 5:30 to 7. We are free.
5:30 to 7. Okay. Okay. Let me see. What is the best I can do in this? I'll maybe suggest some slots and we'll see. We'll pick one of those. I'll send an email after we finish today. Right. Okay. So far we have done like a bunch of things. And I'll still continue our discussion on. So when is the last lecture? Does anybody remember the timelines for the course?
No, sir.
September
Actually,
21, we have the exam. 21 and 22nd.
Yeah, that I know. But do we still? Okay. Anyways, let me check the timetable. How many classes we have?
On 19th November, sir.
19.
19.
19 December.
November. Last class you are asking, or how?
No. When do the lectures end? When is the last lecture?
That is not decided. I think so.
Okay. Let me figure out what it is.
Sir, just what can be the syllabus in the end sem? It will be after mid-sem or something?
Okay, no, I think what I will do is so 30% will be before the midsem and 70% syllabus will be after the midsem. Because here we'll go formally to a center and write exam, right? So we'll do a 30-70 or a 25-75 kind of exam.
Okay.
Is that okay?
Okay, but will you give us the syllabus in that case, or
I will do that. I will do that. Yeah.
right, okay. Okay.
Exam is similar to MCQ or
Yeah, similar to MCQ, MSQ, and numerical answer. I think you have to go to a exam center and write, if I remember correctly. It won't be online proctored exam, but I think you have to go to a center and write. I'll check also on that. What is the provision for the answer? Okay, so I'll post post messages on that. Okay, so we were somewhere. Two things we did. One was about minimizing or even a maximization problem. I wrote we can write minimizing fx subject to a certain set of equality constraints, certain set of inequality constraints, and so on. And then we wrote down how to solve this. So we had our Lagrangian, which was, I could actually have several of this, right? Hi, Gj. So Lagrangian would be f plus lambda 1, h1, lambda, I'll call this n, hn plus g1, mu1, g1 till mun, mgm. Right, and then we had a bunch of conditions which were the necessary conditions for optimality called the KKT conditions. And we did a little example also related to that. Okay, so we'll do a special class of this optimization thing called the linear programming. So in this, so let me start off with by writing a problem. Say I have start with a maximization problem. Of course, the reason I will do this is, and I think a little earlier in our course we wrote down what was a linear program with some kind of a maximizing a profit of a factory based on the number of and different kinds of products it makes. Okay, so I'll just directly start with the math part, that I want to maximize x1 plus x2 such that x1 plus twice x2 is less than or equal to 4. 2x1 plus x2 is less than or equal to 6, with constraints on x1 and x2 being such that they are always greater than or equal to 0. Okay, now I will write this as a thing. So here what you will see is that your objective function is affine. So I can write this as C transpose X, and all the constraints are linear. So in general, this will be of the form AX is less than or equal to B. So the problem I can write of what let me first try solving this from the KKT conditions. What this means. So the objective function is to maximize, I'll call this Z, x1, x2, which is x1 plus x2, such that G1 x1, x2 is x1 plus 2, x2 minus 4 is less than 0. I just have inequality constraints here. G2, again, as a function of x1, x2 is twice x1 plus x2 minus 6 is less than 0. Third constraints on G3 is such that negative of x1 is less than or equal to 0. Fourth constraint on G4 is such that the negative of x2 is less than or equal to 0. Okay, so I will write down now my KKT conditions. So the objective function here, okay, I'm just calling this Z instead of F in the linear setting. So I'll compute the gradient. I think, yeah, okay. So the gradient conditions are that the gradient of L with respect to X, gradient of L with respect to lambda, gradient of L with respect to mu. I'll compute all of these here. So the gradient of my objective function, which is x1 plus x2, will just be 1, 1. Gradient of G1 will be 1 and 2. The gradient of G2, which is this function, will be a 2 and a 1. Gradient of G3, which is minus x1 less than 0 is equal to minus 1 and 0. And gradient of G4 is 0 and minus 1. Right? Okay, so this is so now what are my feasibility conditions? Feasibility conditions are these three conditions here, that x1 plus twice x2 is less than or equal to 4, twice x1 plus x2 is less than or equal to 6, x1 and x2 both are greater than or equal to 0, that they will be in the first quadrant. This condition will give me, this is called the dual feasibility, it's a gradient of L 1 1 plus, or say minus, because I'm doing this mu 1 G1 minus mu 2 G2 minus mu 3, with the gradient of G3 is minus 1 0 minus mu 4 0 minus 1 is equal to 0. So mu 4. Okay, and then the complementary slackness conditions would say that what was that? Those were like mu I, gi is equal to 0. That either the constraint is active or mu is equal to 0. So that will translate to mu 1 of x1 plus twice x2 minus 4 equal to 0, mu2 twice x1 plus x2 minus 6 equal to 0. Third condition is mu3 times g3, that is minus x3 is 0. And last condition is mu4 must be x1. So mu4 minus x2 is also equal to 0. Okay, now we need to find out what are the appropriate x stars and mu stars and so on. So I will write down these conditions again to show that, okay, so the first one will be from writing down equations here. The first equation will give me 1 minus mu1 minus twice mu2 plus mu3 equal to 0. Yes, I'm just writing down the first thing of this equation here, this one. Okay. Similarly, writing down the second equation will give me 1 minus twice mu1 minus mu2 plus mu4 equal to 0. And I know that the conditions on mu's should be such that mu1, mu2, mu3, and mu4 are all greater than or equal to 0. Okay, so these are nice. Let me assume that, okay, since I have equations in mu1, mu2, mu3, and mu4. Okay, so what I know about, yeah.
How did we arrive at this mu1, mu2 equations that grade below the gradient one?
These ones?
No,
This
above this one.
This one.
Yes, correct.
Okay, so this will just be that, okay, what is the first order conditions? First order condition, so my Lagrangian will be of f plus summation lambda I hi plus summation mu I gi. So the gradient of L with respect to x will have the gradient of f plus or minus whatever you can plus lambda 1 gradient of h1 and so on plus mu1 gradient of g1 and so on. And then we equate this to 0. These are just the first order conditions. So if you remember this, we had written down our Lagrangian in terms of the lambdas and mu's in terms of the Lagrange multipliers. Okay, so this is just rewriting the first order conditions, that a gradient of f plus, so in this case it will be gradient of z plus u1 gradient of g1. What is gradient of g1? This one. mu2 gradient of g2 and so on until mu4 gradient of g4, and I equate this to 0. That is what is here, right? So this is the first equation. This is the second equation from the first order necessary conditions. Those are necessary conditions which are essentially coming from the KKT conditions. Okay, now in this, what I for sure know is that, okay, mu3 is greater than 0 and mu4 is also greater than 0. So I can just write down my equations in a little more simplified form as so here, right, mu3 is 0, mu4 is greater than 0. So I can rewrite mu1 plus 2 mu2 will be greater than or equal to 1 twice mu1 plus mu2 is also greater than or equal to 1 plus other conditions that lambda 1 and lambda 2 are, sorry, mu1 that mu1 and mu2 are both greater than or equal to 0. Okay, so this is how we end up with. Now my problem is not yet solved. I just want to find what is the optimal path. So we want to now solve for find values for x1, x2, all the mu's, and satisfy the KKT conditions. Okay, we go to Okay, now what is the geometry of this? If I were to just draw a graph and say, well, I'm working in the first quadrant because my constraints would suggest that x1 and x2 are both greater than or equal to 0. Then I have my first constraint which says that x1 plus twice x2 is less than or equal to 4, which means that when x1 is 0, x2 will be equal to 2. And similarly, when x2 is 0, x1 is equal to 4. So somewhere here, right? So this is my first constraint. Somewhere here. And then this will be the region which will satisfy the constraint. Second constraint is my equation of the form, what is it? Twice x1 plus x2 is less than or equal to 6. So if when x1 is 0, x2 is 6. Okay, this is nice. And when x2 equal to 0, x1 is 3. So something like this. This and this, I just draw these 2 points. Okay, so my overall feasible region is just, I must be, so this I must be around this region. This would be my feasible region, right? Because this equation is twice x1 plus x2 is less than or equal to 6. And this equation is of x1 plus twice x2 less than or equal to 4. Okay, now if I draw the level sets for this, how would the level sets for x1 plus x2 look like? Okay, they will look something like this. Okay, so this could be x1 plus x2 equal to 1, x2 equal to 2, 3, or whatever values. So if for each, I will have some numbers which goes here. Okay, now just seeing the geometry of this, right? So this could be for different values of x1 and x2. So this could be with decreasing values, right? So this here x1 plus x2 could be some number, here x1 plus x2 could be some number, and so on. So which of the green lines under this feasible region, so this region is my feasible set. My x should always lie within this region. You can draw it a little bit. Okay, and then I will choose a green line which passes through the shaded red region to find the maximum of this. Okay, let me check each one of them. Will this line here, will this work? Answer is no, because it is not, the constraints are not satisfied. Will this work? Answer is also no. Will this work? Answer is yes, because the constraint, it goes through the constraint set. Will this work? Something else here? Well, this also maybe, because this goes through, this also will work. So this is fine, this is fine, this is not fine, this is not fine, this line is not fine. Of all the lines, the one which will give me the maximum value is the one which passes through this vertex here. Okay, anything less than this will be a lesser value. Anything higher than this will not be feasible anymore. Okay, so the optimal point is x is 8 over 3, or say x1 is 8 over 3, and x2 is 2 over 3, which is essentially the intersection of x1 plus twice x2 is 4, twice x1 plus x2 is 6. You can check by solving this, that this will be the solution to this. Okay, what do I make out from here, and why is also this a maximum value? Geometrically, it is clear, right? So I can look at maybe other intersection points which are here. This is one intersection point, this intersection point. At all these values, the value of for x1 plus x2 will be always a little lesser. Okay, and then so this is how we solve it. And then if I just want to look at what is my mu1, and then two things, right? So I will always be, so this is not this point where x1 and x2 both are 0 is not of interest, because for sure x1 and x2 will not be 0 is not the maximum, especially when my constraint sets are in the first quadrant, which means that there are two constraints which I had, right? If I go back here, two of these constraints were something like this, and written down something like this. Okay, which means that x1 and x2 will always be greater than 0. Okay, which means mu3 and mu4 will automatically go to 0. So this will mean that, so either the constraint is active or the mu's will be equal to 0. Okay, this just leaves us now to solve for lambda 1 and lambda, sorry, for mu1 and mu2 from this set of equations now here. mu3 and mu4 go to 0. I now just solve for these conditions here. I just put an equality here because my mu3 and mu4 are equal to 0. So I get a nice values for mu1 and mu3, mu2 to be equal to 1 by 3. Okay, so one observation I can make here is the following. So what have I done here? So this is a set of case of linear programming, where the objective function is about maximizing C transpose X subject to AX is less than or equal to B, possibly X greater than or equal to 0. And put this, either I can embed that into the previous constraint or here. Okay, now what will happen, and we'll see a little also empirically, and then later on do a formal proof, is the maxima will not be on any of these yellow points. So the yellow points are the maxima will not be in the interior of the feasible set. Okay, they'll only be at the boundary, and not only that, they will be at these vertex points. What are these vertex points? Let me draw this a little again neatly. So I have this. So one constraint set is this, where so my first one constraint set is x1 is greater than 0, that is here, and x2 is greater than 0. Okay, then I had two lines. One line which was like this, and the other line which was like this. Okay, and all the time, so the vertex points are the ones. So I have four constraints now. This is, say, C1, this is C2, this is C3, and this is C4. So I don't really, so this is my feasible region. I'll just plot this, shade this in green. So this entire green region is my feasible region. These are the vertex points, which are the intersection of the constraints. For example, 0, 0 is the intersection of x1 greater than or equal to 0 and x2 greater than or equal to 0. So, and then I have a constraint. So this is the intersection of constraint number C2 and C4. This is the intersection of constraint C1 and C4. And this is the intersection of constraints C3 and C4. Okay. So one thing is that the maxima will lie on one of the vertex points. So I don't need to compute the entire set. What I need to do is I compute what is the objective value of the objective function here. I'll call this Z1, I'll call this Z2, I'll call this Z3, I'll call this Z4, compare all four, and the maximum will have to be on one of these 4 points. Of course, now that helps because my search set reduces from an infinite point region to a set of finite points. Of course, this is also not very sometimes useful, because if I have, say, some 100 variables and some 200 constraints, then I really still have to search with in a very large search set. So even the number of points would be like in millions, and then I have to compute the objective function at 1 million points and then sort them to find out which is the best value, which is also not. So we need to find a little more elegant methods to solve this problem. So this is where we'll look at, this is the problem of linear programming. And then we look at methods. Of course, there could be like a lot of methods in the market, but we'll do one of the traditional methods that is usually used. Okay, I'll pause for a few seconds here and take questions if any.
Sir, I have one question. So that mu1, mu2 equation that you derived, so why there is inequality? It needs to be equal sign, right?
Where, which one? Okay, let me. Okay,
Downside.
down is here.
Yeah, further down.
Or here you mean?
Yeah, this one, last one. Mu1
Okay,
plus
so
mu2.
here, this is equality only, no?
Yeah,
One.
so in the square brackets which you have given, right?
Correct. Okay.
So
in
why
the
that
square
inequality is
brackets,
there?
in the square bracket, so I'm just reducing it to 2 variables. What I for sure know is that mu3 is greater than 0 and mu4 is greater than 0.
Okay.
Okay, because I'll work around that regions of the exponent. So if I impose the additional constraint on this, that okay, I know that this number here is greater than 0, I can kind of eliminate this number and write this as an inequality.
Correct.
So that's what I'm just reducing it a little bit to make it slightly convenient to solve.
Okay, got it.
Okay, so now this is fine. So I'm assuming 2 things are clear. First is how to use KKT conditions to solve this set of problems. Second is what is the idea of a linear program, and why can we, if we can use some simpler methods to solve this. So we will start off now.
Okay, one quick question on that. On that mu1 and mu2, can you please go to that first question? Yes, so sir, here we have an equation like -1. I'm audible. Hello? Hello, can you please move that?
You can hear a lot of
Yeah, I think someone has unmuted. I'm audible, sir?
You're audible, yeah, go ahead. Okay.
I think there is some noise. Okay.
Well, if you can go on mute.
Okay, sir. So, sir, we have an equation -1 minus mu1 minus 2 mu1 and mu3 equals to 0. And we consider that mu3 is greater than 0, right? So now, okay, so if we multiply it with a -1, so that equation becomes 1 plus mu1 plus twice mu2, right? And minus mu3 would be greater than 0, let's say 0.5. So now if we keep that 1 to the other side, right, that becomes -1.
That becomes
means yes, sir. So means I am not able to understand how the mu1 plus twice mu2 is greater than or equal to 1, because mu3 is not greater than 1, right? It is just a greater than 0.
Hello.
Yeah, it is just, yeah, it is just a greater than 0. So how we decided that mu1 plus twice mu2 is greater than or equal to?
Okay, let me write down if I, so I have 1 minus mu1 minus twice mu2 plus mu3 is 0.
I think, sir, that is -1, right?
Which one?
First one is -1, right?
Okay, let me like this one, right? 1 minus mu1 minus 2 mu2 plus mu3 is greater than 0.
Okay, 1. Okay, I thought that is -1. Sorry.
Oh,
That
okay.
is
No,
just
no, no. I just said, okay. So, okay. This essentially means that, okay, sorry. This is
okay.
the first comes from this part of the equation. Oh, this is not minus. Sorry. Okay.
Okay.
So just I'm
Maybe
just
now I
rewriting.
got.
Yeah.
Okay.
Okay. Okay. Sorry about that.
No, sir.
Okay. So formally define the notion of a linear program. I do maybe let me do like one more example and check and then define few things for ourselves, right? So looking at a linear. So another, I like the blue color better. Okay. So minimize say x minus y. Again, x and y both are real numbers such that y is less than or equal to 3. Y is greater than or equal to 2x minus 5. And x plus y is always greater than or equal to 1. So in any problem, the first step is to look at how the feasible region looks like. Right? Or what are the allowable values of x and y. Okay. So we can rewrite these constraints, and now we'll also appreciate how much we looking at solutions of differential solutions of linear equations of the form ax equal to b help us. So these constraints can be rewritten as 0, 1, 2 minus 1, minus 1 minus 1 times x and y is less than or equal to 3, 5 minus 1. Okay, so this is just writing it in a compact form of the form ax is less than or equal to b. Okay, now first is the feasible region. Let's do, even though we've done this before, let's plot this again. First is, okay, y is less than or equal to 3. So this line will be, say, y is less than or equal to 3. So everything beneath this line will constitute y is less than or equal to 3. Okay, there is another line which says x plus y is greater than 1. X plus y is greater than 1 when x is 0, so it will be somewhere like around here. Okay, and maybe these two will intersect somewhere here. So this is the line x plus y is equal to 1, and I'm now looking at all the things which are around this. Okay, and then the last equation I have is y is 2x plus 5. When x, so y is 2x minus 5. When x equal to 0, y is somewhere like minus 5. So I'll have something an area which looks like this. And then they will intersect somewhere. So again, in this case, I am looking at what is the constraint? Y is greater than 2x plus 5. So largely, I'm looking at this area. Okay. So this area inside here, this will be called my feasible region. Okay, if I just were to draw a boundary, it will be something like this. Then it will be this. Okay, so this is my feasible region, and in general, I can write my objective functions as to maximize find function c transpose x such subject to a times x is less than or equal to b. Okay, I can do a minimizing also. I'll just do so. This is also similar to writing that minimize minus G transpose X subject to the same conditions. So I can write the same maxima minima conditions without much else. Okay, so this okay, so okay, what could be a good optimal point here? If I can say, what is, if I just do based on whatever I learned so far, what could be the good value, which, sorry, is it a minimization or maximization problem? Sorry, let's do it as a maximize X minus Y. So what could be a good value just based on whatever I told you so far?
Intersection points.
Intersection points, fine, okay. But still, what are those points? Which one will X minus Y be maximum here? Will X minus Y be maximum here, or will X minus Y be maximum here?
The centroid of it.
No, okay. So it will never be in the centroid. So so we'll again do a formal proof of this. So whenever I'm doing linear program, the maxima will be on the intersection points of the constraints, always. It will never be inside here. It will not be here. So maybe I'll draw in red. So this red points are the points which are not allowed, or they don't. The maxima will not be on any of these red points. It will not be in the interior of the region. It will also not be on the boundary of the region. It will be at the intersection of these two points, or any of these two lines.
So how about minima? Is that the same condition?
Minima will be, if I were to write minimize X minus Y, then minimize X minus Y is the same as doing maximize Y minus X. Okay, just put the minus and you'll get the maximum. So minimum of a function fx will be maximum of the function minus of fx.
Those also will be one of the coordinates of the triangle?
Which ones? Coordinates of the triangle will just be intersection of these three lines. What are the three lines? I have y equal to 3, which is the first line. Second line is y equal to 2x minus 5. Third line is x plus y equal to 1. Okay. So in this thing, it turns out that the point 2 comma minus 1, 2 comma minus 1 is the unique optimal. Okay, I can do this a little graphically by saying, okay, how does any point x minus y equal to c look like? It'll look like something like this. So okay, let me see if there are any other nicer colors to choose. Let me just do a blue. Okay, so this I can start from here. Let me start from here for some value, right? So this could be x minus y equal to 4. Then I'll have something which is like x minus y equal to 3, which passes through this point. X minus y equal to 3. Then I will have something else, which will be x minus y equal to 2. This will be x minus y equal to 1. But there'll be one point where it will be maximized. That is when x minus y equal to 3. And that is also this point, right? This will be the point 2 comma minus 1, where x minus y is 2 minus 1 equal to 3. Okay, graphically, again, my maxima has to pass through the intersection point. It will not cut through points like this. That is not allowed. And also for obvious reasons, right? So you can just see it graphically. Okay, so yeah.
Yeah, my question is, if one of the coordinates of the triangle is minimum, can we say the maximum will lie in any of the other two?
Yes, you can say that.
Okay.
You can just cast it as a negative of the maximization problem and check maybe the minima will, therefore, if I just keep on 4, 3, 2, and then maybe the minimum point will be something like this here, around this, which I'm just drawing now.
Sir, without calculating the value, by seeing the image, can we say at which point it will be maximum or minimum?
No, without
This
without
case,
computation, cannot say. So only thing what I can say is that even though all the region inside this triangle is the feasible region, the maxima, the search for maxima reduces to searching around these 3 points. This is point number 1, point number 2, and point number 3. So I've reduced my infinite searches to this search set of 3 points because there are three constraints. Now,
okay, I can solve those 3 points. I can find maximum or minimum.
of course,
Okay.
if I give you say 200 constraints, you may have to compute at 250 points. That may also not be very easy. So we'll try to have different methods, some simpler methods to compute those optima, computationally efficient methods.
Sir, one quick question. So as we are having a 3 constraint and here 3 intersection points, means it is possible to have a 3 solutions for those equations, right?
It is possible to have 3 solutions for those equations, yes, because you have 3 equations and 2 unknowns. So this is xy is a solution. This is a solution. This is also a solution.
Yeah. So means while solving this particular ax plus ax less than equal to b, shall I get all those 3 solutions, or do I need to solve it individually? Means do I need to first
So
consider
okay,
2
we'll
equations?
come into methods of how we do that. For now, let us convince ourselves that the search for an optima reduces to comparing the value of the object along the vertex points. So these are the vertex points.
Okay. Okay, sir.
How to do that? We'll do the details very soon. Okay. Now suppose in the same problem, let me say that just keep this here, and I say, well, I just eliminate one of the constraints. Let's say this constraint does not exist, so I am left with maximizing x minus y subject to y is less than or equal to 3. You can just draw and check something else. X minus y is greater than or equal to 1. What will be the maxima of x minus y? Now this is my feasible set. Can somebody say some answer? You can just use this picture and take it as a hint. The hint is whenever I ask a question, it will be a little tricky question. So you can have so there is no obvious answer for that.
Only 2 constraints are given, so it's not a closed area.
Okay, it's not a closed area. So what is my constraint set now looks like? This is this. So my first point is this is y is less than or equal to 3. X plus y greater than or equal to 1 is here. So my region is this entire open region, right? So there will be no maxima because each point I find, I can go one better all the time, right? So I can go to a point 100, 0. 100, 0 is in the feasible set, right? I can also go to 10,000, 0. That is also in the feasible set, right? So here I can make x minus as large as I want. Okay, and then there will be no bound. I can just keep going any direction to around this, right? Here, as long as I am inside this and I'm going to the right of this, and I can just keep going it all the way till infinity. So these are problems which are unbounded, right? So like the maximum doesn't exist. It's like if I do profit maximization in my company based on this, I can possibly make infinite profits. Okay, that's not possible. This is only for mathematical illustration. So let's see something else. Now, again, you can draw pictures and check for this. Same problem, maximize x minus y over x comma y, subject to y is less than or equal to minus 3. See the constraints carefully. Y is greater than or equal to 2x minus 5. And the last one is x plus y is greater than or equal to 1. Okay, what could be the optima in this case? In the first case, I had to choose between 3 points, and one of those points gave me the maxima. I could just do that graphically by just plotting the level sets. In the second case, I observed that my region was unbounded. It was not a closed region. So my maxima of the function was unbounded. What happens here?
So it is also unbounded.
It is also unbounded. Okay. Any other answers?
Solution.
Section.
Okay. So the first thing would be because I can do this graphically, it's a small problem. I just plot each of these regions. So x plus y is greater than or equal to 1. So that will largely be this region, right? This region and the arrows here. Okay, then I have y is greater than 2x minus 5. That will be another region like this. Okay, which is this one, correct? So this line is x plus y equal to 1. This line is y equal to 2x minus 5. And then I will have y is less than or equal to minus 3. Okay, y is less than or equal to minus 3. Okay, why did we call this unbounded? So tell me one point which satisfies all these three conditions. Okay, let me arbitrarily choose a point. Does this point satisfy all three conditions? Point number 1. Does point number 2 satisfy all these three conditions? Does point number 3, which is here, satisfy all the three conditions? Does point number 4 here satisfy all the three conditions? Which of these satisfies all the three conditions? Okay, so look at it carefully. Point number 1 does not satisfy y less than or equal to minus 3. Point number 2, it does not satisfy any of these three conditions. Point number 3 also it doesn't satisfy. Point number 4 only satisfies the red the red region. It doesn't satisfy this. So problems of this kind are also known, or these are what I can call, these are largely, this is an inconsistent linear program. Okay, because there is no feasible region here. Right? There is no optimal.
Sir?
Yes, sir.
So these the two lines you drew, right? X plus 1, x plus y greater than 1, and y is equal to 2x minus 5. It is to extend it on the bottom, you will find a region that is common between the red one and the black one, right? Two regions.
Yeah, but
and you will get 2 points actually, correct?
No, but this is the region which is, you see this little cone-like region that will satisfy these two constraints.
Correct.
Okay, and this region here, the red one, will satisfy this one. Now I can extend this further, but this region here does not satisfy constraint 1 and 2. Okay, 1 and 2 is only in this cone here, in this purple region, only this area here. So here there is no optimal, because there is no point I can find which will satisfy all the three constraints together. Right? There is no optimal solution.
Okay.
Because it's impossible to satisfy all the constraints. Okay. Then the point is, okay, there could be, so what the idea here is to show that, well, if the problem is neatly posed, there exists a solution, then my search set reduces to searching around these 3 points. There are conditions if the constraints are not well defined, and in that case, I have something not very nice, that my objective function can go unbounded. Third is there is no feasible region. There's no feasible set where I can say, well, none of the points will satisfy all the 3 conditions. This problem is not even solvable. Here, at least the solution exists; it is unbounded. But in the second case, it's even more. In the last case, it's even more hopeless. Okay, so these were about the constraints. Okay, so let's go to, okay, now what can we say about things in general? Okay, so here let's say I'll just do something very simple here, right? So just recall of solutions to linear equations. Okay, if I give you equations of the form 3x plus y is 6, x minus y is negative of 2. I know a bunch of ways to do this. I'll do this, pivoting, Gaussian, or whatever elimination methods to write this as a set of equations. So this is, I do a set of row column operations. I get a 1, 0, 0, 1 as 1 and 3 to get the solution that x equal to 1 and y equal to 3. Of course, I'll not go into the details of this. Things get slightly different when I have equations of the form 3x plus y plus 5z is the negative of 6, x minus y plus 3z is the negative of 2. Okay, so I can write this as 3, 1, 5, 6, 1, minus 1, 3, and a minus 2. Okay, I can still do all the pivoting. I'll pivot around this x and y. I can write this as 1, 0. So, okay, first is how many solutions will this have? This will have an infinite set of solutions, right? Okay, so I can write this as 1, 0, 0, 1, 2, minus 1 as 1 and 3, in which x and y kind of seem solved. So x equal to 1, y equal to 3, and maybe z equal to 0 solves this thing. That solves both of these equations, right? And then now, in this case, we will call x and y as basic variables and the z as a non-basic variable. Okay. Now, why should I only do this? Why can't I do in terms of z? Why can't I just have y and z as the basic variables? Okay, nothing stops me from doing that. I have a 3, a 1, a 5, 1, minus 1, 3, 6, and negative 2. These are my basic set of equations. I can transform this also to 0, 7 by 2, 1 by 2, 0, 1, and 1 by 2. Okay, here my y will be equal to 7 over 2, z will be equal to 1 over 2, and x can be whatever, right? X and x can be, so the non-basic variables we set to 0. Here my y and z are the basic variables, and x is the non-basic variables. And then we set it to 0. So solutions will be of this form, either this or of the form this. And I can do again the same exercise by setting x and z as the basic variables, and then set as non-basic variables. Okay, now, okay, why am I doing this again, and why am I interested again when I'm talking of linear programming with a set of linear constraints. Why am I interested again in coming back to this one? Okay, I'll just take a little pause, just see if you have any questions.
The basic variable, like the non-basic, is it same as the free variables?
A free variable, yeah.
Free variable.
Free variable, yeah. It's also the same as the free variable. Okay, I'll do one example, and maybe from the context of what we do in linear programming. Okay. Right. Okay. So suppose I have a set of constraints. Of the form x1 plus x3 plus 3x4 plus x5 is 4. Then I have x2 plus x4 plus x5 equal to 3, and again x3 plus x4 minus x5 equal to 1, and all this x1 till x5 will be greater than or equal to 0. Okay, so what I would know is that my rule number 1 would be at least one optimal solution one optimal solution is a vertex of the feasible region. Okay, and all vertices of the feasible region are basic solutions to the system of linear equations. Okay, what do I mean by this? Okay, so I have this now, this system of linear equations where I can write this as ax equal to b of the form my a is 1 0 1 3 1, b is 4 3 1. This will be 0 1 0 1 1 0 0 1 1 minus 1. So I'm just writing down this as a matrix expressions. Okay, now what is a basic solution, right? What I would want is to get it in this form, right, where I'll have an identity in setting y and z as basic variables, or as in this case x and z as basic variables. So I do a little row operations. So let me say, ask myself if I can set this to 0. So I do an appropriate row operation that I subtract third row from the first, right? I subtract third row from the first. So what I get is my A will now look like A will be 1. R1 is R1 minus R3. So 1 0 1 2 and a 2. Okay, what I'm doing is set R1 to R1
0.
Why 0 0? I'm doing R1 is R1 minus R3. So okay, this will be 0. Sorry.
1, 2 will be 0.
Yeah, okay. Then I have 0 1 0 1 1. I'll have 0 0 1 1 minus 1. Here I'll have again same R1, so this will be 3, this will be 3, this will be 1. Okay, So my basic variables are x1, x2, x3. These are my free variables. So set x4 equal to x5 equal to 0. My solutions will now nicely read x1 is 3, x2 is 3, and x3 is 1. Okay. Okay, I can also do the same by setting the basis as, say, x2, x3, and x4. Okay, then what I get is, I'll skip the row column operations and just write down the solutions. So what I get, I'll get minus 1 by 2, minus 1 by 2, 1 by 2, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I will have 0, minus 2, 1 times x is 3 over 2 minus 1 over 2, 3 over 2. Okay, so this will give me a nice solution of the form x2 is 3 over 2, x3 is minus 1 by 2, and x4 is 3 by 2 with the non-basic variables x1 and x5 both going to 0. Okay, so okay, now is there a problem here? Okay, now let us look at the solutions, right? And what were my constraints? Constraints were of the form. So I get two solutions. Let us look at these solutions carefully. Is this solution feasible? Like, is this vertex point feasible? Okay. And second, also look at that. Is this vertex point together with x4, x1 equal to x5 equal to 0? Which of these two are allowed? Which of these two are not allowed? It could be that everything is allowed and nothing is allowed, or one of them are allowed. Is there a problem in any of this?
First one is allowed.
This is
Because
fine.
x1
Second
to
one is not
x5 should be greater than 0.
right. So this is a problem, right? So this is like not feasible. So I don't need to search for the maxima around this vertex points, right? We don't want a basic solution. What we want is search for a basic. Shankar sir, you're going home. Okay, this is Shankar sir. Is a basic feasible solution. Okay, so what I'm doing is now, right? So if I have a situation where I have, say, a set of vertex points, 1, 2, 3, 4, and maybe 5. Okay, so maybe my feasible region will be inside of this whatever this is, a hexagon. Okay, so now the point is, I start with one basic feasible solution. I should only move in those directions which will give me an improvement in my objective function, and also which does not violate the feasible condition. So for example, here I start with x1, x2, x3 being my basic feasible solution. Can I go to any other solution? Would mean that you are putting one of the variables to 0. So here x1, x2, x3 are my solutions. So here x1 goes out, x4 comes in, right? x1, x2, x3. So x1 is out, x4 is in, but then this is not a feasible solution. Now somebody has to tell us of what is the right direction to move. I don't want to move in directions which will give me a non-feasible solution. For example, if I go back to this problem here or here, if I start my search here, if I start my search at this point, the next search should not let me to go to this point, because this is not a basic okay, this does not satisfy. If I in addition, if I impose a constraint that x and y must be greater than 0, this will not satisfy that constraint. Okay, so I have to go search only those points which are meaningful. Even though now my search set is reduced to only a finite number of points, I should eliminate points which do not make sense for me. Okay, now how do I eliminate points? How do I change my feasible solutions and so on? Okay, I'll do a little exercise here, and I think we just go. Okay, sorry. Yeah.
One question.
Yes, sir.
So those are 5 dimensions, right? So we cannot visualize those in terms of area.
Yeah, I cannot visualize this, but I can just try to do the visual explanation just based on what I see. But here what I can say that is, how do we look at solutions of these equations? The solutions are we are just looking for the vertex points which will constitute my basic feasible solutions. In my 2D case, I can just look at these vertex points. Higher dimensions, I am unfortunately not able to draw those things.
Okay.
Okay. So now, how do we move from one basic feasible solution to the other? Okay, so let me start with x1, x2, x3 as my basic feasible variable, which means my equations now look like x1. Okay, so from these are my basic variables. x4, x5 are my free variables, so to speak. So which I said x4 is 0 and x5 is 0. Okay, now which direction I want to move? Should I make x4 to be non-zero, or should I make x5 to be non-zero? Okay, let's say for argument's sake, I just do a lottery and say that let x4 remain 0, and then we'll see what happens as x5 changes. Okay, so I still keep my equation. What were my solutions? Were that x was equal to, where x1 was equal to 3, x2 equal to 3, x3 was 1, x4, x5 both were 0. Okay, so my equations now become, so I'm just rewriting this here from here, right? Just for a movement, observe these equations. I'll start from here and see what happens as I move along the direction of x5, keeping x4 equal to 0. Okay, so my equations now become x1 plus twice x5 equal to 3, x2 plus x5 equal to 3, x3 minus x5 equal to 1. Or in other words, x1 will be 3 minus 2 x5, x2 is 3 minus x5, x3 is 1 plus x5. Okay, so I want to get x5 into as my basic variable. So I'm just moving. So what directions I can move? All my constraints are such that x is all x1 till x5 should be greater than 0. If I keep increasing x5, what do I violate? Well, if x5 goes from 0, this never violates. Okay, what will happen when x5 is equal to 3 by 2? When x5 equal to 3 by 2, x1 becomes 0, and for all other values, when x5 is larger than 3 by 2, x1 will become negative, which is not allowed. So if I were to get x1, so x5 as my basic variable, then the point that drops x1 drops to 0 first as x5 increases. Okay, so x1 is now out of the basis. So the new basis now, new basis now is x1 is out. We kept x4 equal to 0. New basis is now x2, x3, and x5. Okay, this will give me the value of, I can just do my computations and check what happens. This will give me x2, with some value, okay, some values which will give me the feasible values, right? Okay, so similarly, okay, well, how do I do this, right? So if I can just compute these numbers, right? The first number will give me 3 by 2. I'm just computing these coefficients. Let me write this in, right? So this, and this. Okay, the first coefficient is 3 by 2. Second coefficient is 3 over 1. There's just a 1 here. Third coefficient is minus 1 by 1, right? So this is a negative value, doesn't matter. I can just keep on increasing x5 with never having to violate x3 is greater than 0. So I just look at the smallest number here, which is 3 by 2, and say, well, the first one or the one to leave the basis would be the one where the ratios are the smallest, right? That is, x1 will leave this basis. So this will be the strategy for me to move or just check what happens when I move from one basic variable to the other. Okay, yeah. Nirav left for home. Okay, so sorry about that. Okay. Right. Okay, so I'll just maybe stop here. So what we have looked for is, if I have a set of basic feasible solutions, how do I move from one to the other? Okay, and next we will see how in what does this mean in terms of solving a simplex problem. That will take a little more time. I can't do that in 5 minutes, but I will just stop here and maybe try and take some questions.
Sir, how we have got these 3 equations, if you can repeat.
These 3 equations? Okay, good. Just look at this one, right? Okay. The transition from here till here is fine?
Yes, sir.
Okay. So here I have now 3 basic variables, that is x1, x2, x3. x4, x5 will go to 0.
Okay, got it from it.
Yeah. So what I want to see now, I can do the same for x4, right? Say suppose now let's do as an exercise, right? Let's say now what did I do here is I just I let x4
equal to 0. Now we let x5 is equal to 0.
And just check what happens when x5 increases. Now do the converse. Let x5 be equal to 0 and check what happens when x4 increases. Which one will be the first one to go out of the basis? So I can write down equations now that x1 plus twice x4 is 3, x2 plus x4 is 3, and x3 minus x3 plus x4 equal to 1. Just check what happens as x4 increases, which one will go to 0 first. This is the same thing that what we do for. Okay, now we will try to take all these things that we learned in terms of basic solutions and basic feasible solutions, try to club them to now solving an optimization problem that we can do, and that is what we will call as the simplex method. I mean, I'm sure people would have heard of this and would have also done this in different ways, but we'll learn it in a little more general fashion now.
Sir, after solving
One question I have.
yeah, go ahead.
So one question that I have is when you are making this, about this basic and non-basic variables, right? Working out the solution. So you are equating all these things to the actual, like a system of linear equations, right?
Yes, yes,
But
yes.
but when we make this kind of a basic, non-basic part, and then we make that equal to 0 and then do it, but then you're transitioning from that basic, leaving from that to another. In that case, will the first time when you showed that objective function, right, less than or equal to things like that, that will that modify that objective when we say, x plus y plus something is less than or equal to 3 or something like that?
Correct. Okay, so maybe I'll just write down the problem. I'll not do the solution for that. Let's say I am doing a problem of, let's say, around the same points, in the same constraints. I want to say maximize x1 plus x2 plus x3 plus x4 plus x5. Okay, such that all my constraints, which I can just write down a set of constraints. So what I would see is that first is look at the vertex points. Okay, and just see first is then look at the basic feasible vertex points. Of course, it will not be feasible because I'm working around the feasible sets. And then how to, so suppose these are the 5 points that I need to check, right? So I will need to go from one point to other, and will actually should go to the point. Suppose the objective function here is 6, and say here it is 4. Okay, so this direction does not help me, right? I should only move the direction which goes from a 6 to a 8. Okay, suppose this is the maximum, right? So maybe I can start from here and move in this direction. Somebody should also tell me when the algorithm should terminate. So those things we will look at a little more formally when I do a proper problem on this, and then we'll do with the help of an example, and then have discuss on a general method for that. Okay, that will come up. So you have to maybe wait a week for that.
Sure. Thanks.
Okay, so I'll so assignment 1 you people submitted, right? Online.
Yes, sir.
Yes.
What about assignment 2?
So assignment 2, for that there was no
Submission link.
link.
Okay.
I mean, there was no assignment on the portal. Like whatever you had sent me, like that was.
Okay. But you people have solved it, right? So if I can ask you to submit in like 1 or 2 days, you should be able to do that.
Yeah, I think yeah. Some people are. I mean, some questions are still left to solve for many. So I think we can submit it by this Friday. I think that should be there.
Okay, fine. Okay, I'll do
Friday,
that.
Saturday. Yeah.
Sure. Okay, no problem.
And there is one more, like
Sir,
one
please,
more
sir, please
assignment.
make it at least, or miss the deadline for assignment 2 at least till Saturday.
Okay,
So
I'll
that
do
at
it for
least we
Saturday.
get some time.
Okay, and the assignment 3, what you can do is you can go through the problems, and on Friday when we meet, we will discuss how to solve those problems. I will not solve by hand myself, but I'll just tell you how to approach those problems so that the learning will be a little more constructive. So read through those problems and tell me specific problems which you would want me to, or where you need hints to solve. Okay, so we'll just discuss the assignment 3 problems. Maybe a couple of them I can solve here, and then the remaining can do it when you get time.
Sure.
Maybe I'll get my TS to do that. Okay.
Yeah, sure, sir.
Okay, good. Thanks.
Sir, one doubt. In
Yes,
this
sir.
question, the last question that we have solved, so we have taken x4 equals to 0, and we are slowly and gradually increasing x5 value. So after that point, we are checking which value is getting out of the feasible region, which is the first value. So
yes.
the value which we got is 3/2 for x1. So we are replacing x1 with x5.
Yeah, now we're saying x1 is no longer the basic solution. x5 comes in, and only 3 are possible, right? Because I have 3 equations. Only 3 basic solutions are possible.
Correct. So we need to repeat the same process for x2, x3, and x5 going forward.
Yes. So we will do a little more constructive method. At least now I know. So if I have 5 variables and 3 equations, only 3 can be pivot variables, right? And 2 have to be, or 3 can be basic variables. 2 can be free variables. Okay. Now I think, how do I nicely choose which are the basic 3 variables for my solutions?
Okay. So my
Yeah.
question was one more like x3 value already we are getting as -1. So can't we remove x3? Because
Yes,
x3
okay.
value
We'll
needs
see.
to be
Okay.
removed.
Okay. All that questions will answer of which one to remove and which one not to remove. So that is we'll learn it a little more constructively. At least now I know how do these points move and how do I switch from one basic solution to other and what happens in that process.
Okay, sir. Yeah.
Okay. How to do this? I will maybe start with an example and we can work from there.
Sure, sir.
Okay. Yeah. Good. Thanks.